Okay. Hi everyone. Welcome to the Towson University Software Engineering Club workshop. Today we'll be going over designing a database. This is part one of two for the database workshop. The second part will cover building a database application. This will be written in Java. And it will happen on Thursday if you're here live. If not, it will be uploaded to the YouTube channel. Um, I'll be going over more details on that one after this. In the meantime, if you are following along, you'll have to have MySQL server and MySQL community workbench. If you do not have those, it will be very difficult to follow along because that's what we'll be using. Any and all SQL written will be written in with MySQL. So if you are using some other SQL um, driver, it probably will not work exactly as shown in this video. But if not, um, that's fine too. It's sort of all the same, really. You'll also need Java 15 and the Java database connector driver for the part two of the workshop. That won't be needed today, but it's good to have ready in case you want to follow along for that one too. And before we start designing the database, we need to talk about what exactly a database is. So, what is a database? Let me get this out the way. Um, A database is pretty much a structured set of data that's used to electronically store data. Um, and what that pretty much means is you can think of it as like a digital warehouse. So picture a real warehouse, like an Amazon warehouse. Warehouses are usually organized. It's pretty easy to find what you need in most warehouses. And that's sort of how we think of a database. We picture a database as an entire warehouse, and that warehouse may have data that's defined into let's talk about like Amazon warehouses, for instance. Cooking appliances or cooking utensils like spoons, forks, books, or that could be textbooks, that could be just entertainment books, any sort of books really. Video games, that's something that would also be in a warehouse at Amazon most likely. And there's tons of things at Amazon, A to Z. But the goal is that if you were to look for something in an Amazon warehouse, you'd probably have an easier time finding it if you knew where it was and what header or what kind of data it was. So if you were looking for a book, that would probably be under the in the book section of the warehouse. Or if you're looking for the latest video game, that would be in the video game section of the warehouse. So you can select the video game from the video game section of the warehouse. And that's essentially the main idea of databases. It's designed in a way to make data, to store data, keep it organized, so that way it's easy to retrieve that data and whenever we might need it. Um, so databases, they're typically used in web applications, nearly all of them. But typically you can see databases being used in other applications. If you ever worked at like a job or internship, they might have their own local database going that they use to store different things. So this could be like passwords to different systems or servers. They could probably keep like an archive of just like old things that they've made in a database. Um, but typically they're in web applications. So if we look at social media, for instance, Twitter, when you go to log in with your username and password, it usually verifies and authenticates that based on information stored in the database. So and that's usually probably stored in like a authentication table or some sorts. I'll go over exactly what that means, but in a way, you can think of database as a warehouse. Um, so that's the best way I figured out to understand databases is just to get it as a warehouse. Um, and just like warehouses, they need to exist somewhere. Um, so like an Amazon warehouse could probably be on I don't know 423 Main Street. There's an address to a warehouse, and that's where the warehouse lives. You could think of the same thing for a database. It needs a computer or a machine to live on. It needs a server to live on. Databases can be hosted on the same machine or same computer as the application interacts with. So, for example, if I'm Twitter, I can have the Twitter application, like the backend to Twitter, can be on the same computer that the database is on. It probably isn't, but it can be. They're usually hosted on separate machines, so I might have computer A that hosts my web application and computer B that hosts a database that the web application interacts with. Um, Applications that would like to use it will have to connect to this machine, so they're two separate computers. They don't know each other locally. unless they're like plugged in through like a cable, which usually isn't the case. Usually they connect through some sort of transfer protocol. Uh, Maybe it's most likely not HTTP, but it might be. I'm not exactly sure on the specifics of how they connect, but databases basically need to be connected to each other, and we'll go over what that means too, and we'll see a little bit of an example with it. The database we'll work with today is going to be hosted on the same machine. It won't be hosted on a separate machine, so we won't have to worry about that specifically. But I will go over the connection process. It's the same whether it's on your machine or a different one, essentially. So um, yeah. So a couple of database use cases just to make it a bit easier to understand. I went over with Twitter, storing user login data as well as user authentication. When you go to create your Twitter account, you will usually put in like a username and I believe a password and an email and a phone number maybe. Um, all that gets stored in a database. It may not be stored in the same table. Table you can think of as like that section of the warehouse I was talking about. So like the video game section, the book section, or the cooking appliance section. The user login data, like the username and email and phone number, might go stored into like a user table, and it's probably typical for like the password hash, not the actual password, but the password hash to be stored in some other table, and they exist via some relationship, which I'll also go over eventually too. Um, you can also store key data that's used for web applications to work. Um, I'm sure everyone's heard of cookies. Cookies are just data that is stored locally on your machine that helps the web application work. When you're logged in, one form of authentication is cookie authentication. And what that means is basically it'll store I believe it's different between most applications, but typically you might see a session ID or a session token, which is just some randomly generated string that authenticates your login instead of like putting your username and password for every web request you make. Um, you could also couple it with like your user ID, a username, just so that's not to query the database to get them every time it needs your username. Um, so that is an example of key data that your username and user ID is obviously stored in the database, but something like a session ID needs to be generated when you log in, and then it needs to store that in a database. And when you're done with it, it will uh, invalidate the ID and generate a new one when you go to log in. Um, Another example, if we go back to Twitter, storing tweets on Twitter. Um, when you go to make a tweet, it's not just existing somewhere floating in cyberspace; it's stored in a database. How exactly Twitter stores their data is completely a mystery to me. Um, or you can store the file path to a profile picture. So when you make a profile picture, 9 times out of 10, they're not storing the actual photo in the database. The photo is getting saved somewhere on some system, and the path to your profile picture is stored in the database. So when it needs it, it can just pull that file path and load the photo in. Does that make sense? Are there any questions? If there's questions, you can ask in chat or just use your microphone. Take that as no questions. Again, if there's anytime anyone has a question, just feel free to use your mic or type in the chat and I'll answer as soon as I can. Let's go over database structure. So if we go back to our warehouse example, we're picturing an entire warehouse. It's when you typically warehouses store individual items that belong to one company or one entity. So an Amazon warehouse will usually store things used by Amazon. I can't really think of another example, but like if you think of like a food warehouse, right? Food store that could be used by virtually any grocery store, really. So that could also be used by them. Um, that's sort of the idea of what a database schema is. So a schema represents one physical database or one physical warehouse, which represents a database. So when we're saying the Twitter database, we're talking about the Twitter database schema, which is full of tables. And each schema can have multiple tables, and tables are where the data or your object is physically stored in the warehouse. So if you go back to the warehouse example, the tables would be the sections of the warehouse. So the video game section would be called the video games table, and that would have different video games or different pieces of data. The cooking appliance section would be the cooking appliance table, and so on and so forth. Ideally, data and tables should be related to one another. So you don't want to put the cooking appliance section or some item that belongs to cooking appliance in the video games table, because that defeats the purpose of the database. It's not organized. It makes it harder to find. Imagine you want to go get that appliance and it's in the video game section, when in reality it should be in the appliance section. Think of it as if you're going to the grocery store. Typically you might see like a food item packed somewhere it shouldn't be. um, Maybe someone might be looking for that food item and it's sitting by the sodas when it should be with the meat. Um, so that's just a typical example that happens in the real world. This isn't allowed to happen in databases. Technically, the database won't allow it to happen, but if the user designs it bad, then it can happen and it shouldn't. um, Another important concept with database tables are relationships. Relationships are what relates data together. If we go back to the Twitter example that I mentioned earlier, I mentioned that the user information like the username, username, email, and password or phone number are stored on its own table, and the password or the password hash is stored in another table. Well, the database doesn't see any sort of relationship between the two. It has no way of telling that, oh, this password hash belongs to this user unless you give it a relationship. And what relationship really means is that we couple some sort of identifier from one database table to another. So instead of just having usernames, emails, and phone numbers on a user's table and just password hashes on the password table, we'll store password hashes along with the user ID that comes from the user ID table or the user table. So let's say I was a user, my ID was 3, and there's another user whose ID is 7. So the password hash table would have the data for the table will look like the password hash, and it'll have a column with the number 3 in it, and that would just mean that that's my password hash. And then there will be another password hash with the ID 7. That means that that's the other user's password hash. And that's sort of what relates data together. If it didn't specify a user ID, there'd be no relationship. There'd be no way for data to tell, or there'd be no way for the user to tell whose password hash that belongs to. And that's very important for databases. It's sort of what makes them work. Without it, databases would be a lot harder to work with. Sometimes, in some cases, impossible to work with. So relationships are important, and we'll dive into that more. And in fact, we'll design, I believe, 3 relationships for our database structure or our database schema. So yeah. Any questions on that? And does that make sense? Um, Again, questions, you can say it in mic or put it in chat. All right. Take that as no questions. Go ahead and move on. Going to dive deeper into database tables. Each entry in a database table must have a unique identifier. This is known as a primary key. If you go back to the previous example I was just mentioning, the user ID 3 that I said earlier, and the user ID is 7 for the other user. I made these distinct values just to make the example better, but it's also because they have to be distinct values. I mentioned earlier how the database won't have a way to tell what relationship exists without a unique identifier. This applies to just tables as well. So each entry of data, if it doesn't have a primary key, the database can't really tell what's different data. So if we go back to our warehouse example, we know what's different data because we'll see 2 physical like kitchen appliances or games in the actual warehouse. But the database isn't a physical thing. It's just data, which is just electricity. It's either high voltage or low voltage. So it doesn't really know what physical things are. And this is why we give each entry in a row a primary key. This is usually a number. It could be a letter. Most of the time it's a number. And we've seen this before, really. If we look at user IDs, for instance, that's usually the primary key for a table, or for a database table. I can't think of any other examples really, because usually the primary key is hidden away from the user. Most of the times it's just user ID. It can also be like a ticket number. So if you have like a plane ticket or a movie ticket, they have like an individual number. With that data stored in the database, that would be its primary key. because again, they're never the same, so it's always different. So the database always knows something different. Um, a table can have multiple kinds of data with varying data types. So if we take a look at the kitchen appliance or the video game database table, when we're looking at our video game, it has a couple of different things to it that make it a video game. It has a serial number, which is its primary key. Um, it has a disk, a title, um, a box art case, maybe. It has a couple of things that really make it stand out and make it different. So, for example, I mentioned earlier the box art and the disc. They're physical different things. So, like a case and a disc work very differently. If you're playing a game, you need to insert the disc into the disk drive. You can't insert the case into the disk drive. They're different things. They're different types. This applies to digital data as well. So we're all familiar with data types. So like we have integer, string, characters. This applies to database tables as well, but this applies differently. For example, integers are called int, and they're either signed or unsigned. Signed pretty much means it could be negative, so it'll have a positive or negative value, and unsigned means it's always positive. So an example of that, user IDs are typically always positive. They'd be unsigned. Um, an example of a signed integer would probably just be like some math operation or some vector with some direction. So that's an example. Strings don't really exist in database tables the way you think they would. Strings are just a collection of characters. So the database table will see it as a collection of characters too. They're typically known as varchar, and they have a max size. So varchar of 1 is just a character, and varchar of 30 is a string or a word that's 30 characters long, or 30 characters max. It doesn't have to be 30, but the max is 30. I believe that's all that's really important about database tables. We'll see more. We'll see more examples of the primary key, and more examples of unique identifiers too that may not be primary keys, but they're also unique. And of course, we'll see that when we design the database. Going to dive into relationships too. Relationships are important. They're very important, as I mentioned earlier. They can help define significance of data. So, example, I mentioned earlier about plane tickets. Um, if if I buy a plane ticket, the database will see that as my user ID or my social security number that's unique to every person owns a ticket number or a unique ticket number for a plane ticket. So what this tells the database is that there's a relationship between me and that ticket number. And what this means in real life is that I own this ticket. This ticket is mine. So when the I don't know, receptionist or whoever at the airport checks my sees I have a ticket or something, they see that the database will show that this relationship happens. Okay, you own this ticket. Here you go. Board your plane, whatever. And that's sort of how it works. Really, it's a lot of times it's down to thinking. If you remember the workshop I did on object-oriented design and intro to programming, I mentioned that object-oriented programming is about modeling objects. That sort of same thinking can apply with relationships and databases, which again makes database design really good if you're making an object-oriented program. They sort of go hand in hand. And relationships can be one of 4 types. I only have 3 listed here, but one of them works vice versa. So there can be one-to-one, one-to-many, or vice versa. So many to many, or many to one, and many to many. An example of all of them we can go over. So one-to-one would be like saying only one person can buy one plane ticket. So this isn't really like typical, I suppose, but let's say I went to an airport and I went to go buy this plane ticket or wherever you go to buy plane tickets at. If I were to buy this plane ticket, that means this plane ticket belongs to me. Nobody else can buy it. No one else can have it. So the database will show exactly one user ID to exactly one plane ticket ID in the relationship table. So that means that any other entries that get added, so they won't be able to have that ticket number that I have. One to many sort of works in the same way, except that if I were to buy that plane ticket, other people could also buy that exact same plane ticket. So, say there's person A and person B, and we want to buy plane ticket A. We both could buy plane ticket A. That's not typical in planes. You can't sell two tickets to different people, but that's sort of exactly how that relationship works. And the vice versa is also true. Many to one. So if I were to buy, if I were to buy multiple plane tickets or multiple plane tickets, that would be like um, me going to buy plane ticket 1, 2, and 3. That's allowed. I can have multiple plane tickets, so that would make sense. But the fact that there's my one user ID is linked to 3 different plane tickets. Um, that's sort of what that means. And also, other people can have that same plane ticket too. And then there's many to many. Many to many is pretty much a if you combine one to many and many to one into one entity. So many people can buy many plane tickets. So if let's say there's a group of 3 people, and we all want to go buy the exact same plane tickets. So we all bought 3 plane tickets. I buy plane ticket 1, 2, and 3. Person 2 buys plane ticket 1, 2, and 3, and person 3 buys plane ticket 1, 2, and 3. That's many to many. There's many people at many plane tickets. Um, it's kind of hard to visualize in person with some of these relationships. It really depends on the situation. Like 1 to 1 is pretty easy to understand with plane tickets, but maybe something like many to one or one to many is kind of hard to understand with plane tickets. Um, but it's all within database design, so you need to think about what works in the real world when it comes to modeling objects. Um, so yeah, and just like I said earlier, relationships need to be linked by a primary key. So my social security number is linked to a plane ticket number. The primary key social security number that identifies a person, and a ticket number identifies a plane ticket, and that's how we link them. Um, are there any questions about that? I know that might be a tad bit confusing to some, so if there are any questions, please ask again, microphone or in chat. I will answer. Okay, going to assume there are none. So, moving on, we're just about to get into the good stuff. Interacting with a database. So databases are interacted with using SQL or structured query language. Um, SQL is a logical language that uses facts to retrieve data or execute some action. So if you attended my the first workshop on intro to programming, I went over 3 paradigms of programming. They were object oriented, which is most people are typical with. That's Java, C++. There's functional, and there's also logical programming. I mentioned SQL as an example, and it is. SQL is not really like a typical programming language that you might see with writing Java or writing some functional code. SQL is sort of just like telling the computer facts about the database to retrieve data. If we go back to our warehouse section, let's say you were an employee at the warehouse and I was some manager or supervisor, and I say, go get me or go select every video game from the video game section. That would mean, okay, that would be very tedious work, but what you would do is you would go over to the video game section, select every single video game, and bring it back. Um, that's sort of how SQL works in a way when it comes to querying the database. We can be more specific. We can say select select just the game. I just want the game discs. Give me all the game discs where the game title is I don't know, Crash Bandicoot. So you'd have to walk to the video game section, select every game disc where the game title is Crash Bandicoot, and bring it back. So that time, instead of giving me the entire video game, you gave me just the disc. You gave me one piece of data from that entire entity. Um, and that's sort of the beauty of SQL. That's what makes it in databases. That's what makes it organized. Is that we can easily retrieve data. It's not easy in person, obviously, but the computer is very fast and very smart. So it's easy to retrieve data and easy to execute on some data. we can insert something into a table. Let's say I bring in a couple of new games and I say, okay, insert this video game into the video game section. Then I give you, okay, here's the case, here's the disc, here's the serial number, here's everything. I would just be handing you the actual like physical object, but the computer talks by data, so I would tell you all the data, and you'd say okay, and then you would go and you would insert the new game into the video game section. I can also say insert this kitchen appliance. It's a stove. It has I don't know, 17 different settings. And you would be okay. I will go to the kitchen appliance and insert this new stove. Um, and that's sort of like the beauty of SQL that allows us to insert new things. We can update. That means change an existing item. We can delete or remove new items or remove items. So yeah, it's database SQL isn't really it's not really a language most people memorize. It's not too hard to get down when you see some of it in person or when you actually code. But yeah, it's okay. We'll go over some SQL. A couple of SQL actually, not like anything extreme. It's very simple. It sounds scary, but it's not. I promise you. I wouldn't lie to you. Um, and to keep my promise, here are some common SQL commands. Um, these are just a couple. There's a lot more SQL commands, but these are some of the common ones. So select X from Y where some condition. So let's break this down. Um, select X from Y. Um, X would be your column, and Y would be the table name. So let's say if we go back to my disk example, I would say select disks from video game. Disk would be just that one piece of data, and it'd be from the video game table. Um, in case you want the entire like video game, you could use the wildcard operator, which is just the asterisk or the star. So select all or select star from video games. That would literally mean give me every single video game, and it would. Um, where condition should be pretty self-explanatory. This allows me to tell the database exactly what I want, pretty much. So I can say where game title is Crash Bandicoot, it would give me every game where the game title is Crash Bandicoot. Or give me every game where the serial number is 1. If we remember, the serial number is the primary key. It's always unique, so it will always return one value, and that would just be that one game, whichever the serial ID is 1. We have insert into tables, so insert into Y and column names and values to insert. So what this means is this is adding a new value into a table, so we insert into Y being the table name, so insert into video games. The column names, so that'd be we would say serial number, disk, game case, box art, etc. And then the values would be the literal values we want to insert. So the serial ID, let's give an ID 4. The box art could be some file path to its art. The name could be I don't know, Fortnite something. It would just be the actual values you insert in the order you wrote them as column names. So if you put column names as serial ID, box art, and disk, the values would have to be in that same order. So serial number, box art, disk, that'd be serial number 3, box art, some file path, and name, I don't know, it could be some name. It doesn't really matter. Deleting from Y, where condition, Y being a table name, condition being some condition. So if we were to delete from video games where name equals Crash Bandicoot, this would remove every single game where the name title is Crash Bandicoot. Or if you did delete from video games where serial number is 4, that would again return one item and it will delete it. So that's the power of primary keys and being unique, is that it allows us to pinpoint one thing, but we can also retrieve many different things. We also need to remember one thing, that relationships can happen within a database. So let's say there was a relationship between me and some game, like I owned this video game and I tried to delete the video game from the database. This entry or this action wouldn't work. It wouldn't run because there's a relationship that I own it. you'd have to break that relationship first. So you'd have to delete the relationship that I own the game first, and then you would remove it. Um, an example of this would be if you try to delete your Twitter account. Um, there is a password hash already stored in some table. If we try to delete my account, the database or the web application Twitter would also delete my password hash from its database table, then delete my account. Um, that way there wouldn't be a linked password. That way a password wouldn't be linked to some account that doesn't exist. That will cause the database to panic, and panics are not good. So yeah. Um, so that's pretty much the gist of database design. What we're going to do now is talk about what exactly we're going to be doing, the interactive part. So we're going to go over this little scenario that I've planned out. This scenario was my project for the database class at Towson that I took. I think it's 455 or 457. It's one of the two. So the scenario is simple. We are working for an upcoming game design company who would like to test data capabilities for their upcoming creative game. The idea is that players can create their own levels and complete levels for points. The number of points is determined by an average rating from individual users. So we need to design a database schema that will provide this functionality. And again, the next time that we meet, we will create a job application that will interact with this database we're going to design. So right now, what we're going to do is just make a database design. We're going to design a schema, create some tables, test out some SQL commands, make sure we got a working database. And next time we meet, we will write an application in Java that will interact with said database. So let's go ahead and share my screen. Okay, so again, if you have Mysql Workbench and Mysql Community Server installed, that's good. We don't even need to do much of Mysql Community Server. We will primarily do all of our work in Mysql Workbench. So you can go ahead and open that now if you want. If you have that, I'm gonna open it now. And assuming you went through all the setup already, you should have something like this. You may or may not have a connection here. If you don't, that's okay because we're going to make a new one anyway. And making a connection is pretty simple in Mysql Workbench. Actually, let me go ahead and open chat really fast because I don't have that open. Okay. Making one's pretty simple. There's this little small plus here. I don't know if you could probably see my cursor. It's right next to MySQL connections. You can just click that, and that'll show a pop-up. We can give our connection a name. Again, if you don't have one, if you already have one, it should be listed. But if you don't, or if you just want to make a new one anyway, that's fine too. So I'm going to name it SEC. That's going to be the name of this connection. You want to leave the host name and port the same. We're leaving it the same because our database is going to be stored on this machine. This will be our server, our own computer. So this is your localhost address and port 3306. This is the default port. Unless you change this in your installation, it should be 3306 still. You can leave it as that. That's fine. You can create a new password username. I'm sorry. You might have it as root. You can use it as root. I'm going to go with admin. Actually, I'll leave it as root. You can change it to anything you want, really. But I'll leave it as root. If you're on Mac, you want to hit store on keychain for password. If you're on Windows, it might say store in vault. But if you want to hit that, it'll ask for a password. This password should be the same password you use during your setup. So when you set up MySQL Workbench or MySQL Server, it asks for a password. You want to put that same password in. So I'm going to go ahead and put mine in, and just hit OK. And if you test connection, you should get a successfully made SQL connection. It'll list the host name, port, the user's root, and it will list your SSL connection, which isn't really important for this, but if you have that, that's fine too. And that's pretty much it. Your connection is working fine. You don't need to worry about this stuff, SSL or advanced. It's not important for this. You can leave connection method as standard TCP IP as well. But yeah, that's pretty much it. You can hit OK, and your new connection will be listed here. You can go ahead and go into it. And if you do, this take you into your database. you get a SQL editor. This will allow you to type in some SQL. Your schemas will be listed here. You only have one unless you've used this before. So you have a schema called sys, which is your system. This schema belongs to just a project I'm working on for my own personal gain. So you won't see this one really. We'll have one. We're gonna create another one. So it doesn't matter. We won't be using any of these schemas that they have for us. Creating a new schema is easy. You can just hit File and go to New Schema or New Model. So it might say New Schema, it might say New Model. Or better yet, what we can do, they actually have an easier way. If you want to go ahead and try to create a new use your system schema, that's also fine too. I don't recommend doing that. Just because it's sort of not it's not intuitive if you're using your own schema. Or if using a schema that's already made, it doesn't really make sense. It's kind of hard to make one. It's kind of hard to use it. But if you're using the latest version of MySQL, there's actually a button here. I forget to add this. I think it looks like a cylinder or something. I think this is, I don't know what shape this is. It looks like a cylinder. If you highlight it, maybe it'll say SQL schema. I'm not sure. But it's right here, right below the tab, and above it's like the first line with the plus on it. But if you hit that, that'll quickly allow you to add a schema without going through all the models and stuff. So we can go ahead and get the schema name. I'm going to name it SCC_workshop. All you really need to do is give it a name. You can leave the default character set alone and leave the collation alone. You might not even have an extra option like me, but you can just leave it alone. And that's pretty much it for creating a new schema. You hit apply, and it'll show you the SQL that's running to create the schema. So this is how you create a schema. If you're in the command line or something, you just run this command, it'll create a schema for you. But we hit apply, and it should work. And we have a new schema here. It has no tables, no procedures, no functions, no views. The views and procedures and functions aren't really important for this workshop. It's just the tables that are. So yeah. We're gonna go ahead and create a table. There's two ways you can really do it. One of them is you can hit right click and go create table. This will bring up some pretty UI that will let you create a table. If you would like to use this, you can, but that's not really intuitive. In the wonderful world of computer science, if you're a database admin, you usually won't be using a GUI to work with the database. You'll be using like the command line. You have to write actual SQL. So we're not going to worry about that, and you can delete that too. Instead, we're going to actually write SQL to create the table. So we're going to do now. It's actually pretty simple. I didn't show this as one of the common commands, but it's pretty simple to create the table. We can start by saying create, and one typical thing before I actually do that, usually SQL keywords are written in all caps. So I don't think it will stop you. Like, it doesn't look like it will stop you, but most of the time they're written as like in all caps. So we will do create table, and we just insert the table name. We're going to start off by making the player table. So create table player. We want to go ahead and create some parentheses, add a semicolon at the end, and we're going to double enter. And we're going to insert our column names and data about the column names. So we're going to have a user ID, which is going to be the player ID. It'll be type integer, all caps. And we're going to specify that it's not null. And what this means is that the user ID can never be null. It's never allowed to be empty. And this is important because every player will have a user ID. This will eventually be our primary key, so you want it to always have some value. Type a comma, new line. We're also gonna have a username. We're gonna write it like that. It'll be type string, but remember, strings don't exist in databases. It's usually just varchar, so varchar. You want to set up parentheses, and we want to give it a maximum size. We're going to give it 30, I believe is what I use. Let me just check that out. Yeah, 30. So what this means is that the username can have a maximum of 30 characters. You can make it 20, you can make it 10. You can't make it 0. It can be 1. It has to be some positive number. We also want this to be not null. because we want every user to have a username. And we actually want this to be unique. So we're going to specify unique. You might be asking, why didn't we make the user ID unique? Isn't it important that the user ID not be repeated? It is, but remember that user ID will be our primary key, and primary keys are always unique. We haven't told this database yet that this is going to be the primary key, so it doesn't know that yet. But we're going to specify that later below. So when you specify a primary key, it's already unique, so we don't need to specify this again. If you did, nothing will happen. It won't like go wrong or anything. So you could if you want to, but it's not needed. The username will not be our primary key, but we don't want two users to have the same username. So we specify unique so that way they're different. But this will not be our primary key. We're going to insert another comma. We're going to give password too. Normally, you don't want to. Normally, it's not secure to store the passwords within the actual user information. But and it's also not secure to store the password in plain text. But this is a local application. This isn't any real information, so we will store this here anyway. In enterprise and within actual practice, you usually want to store this in its own relationship table, and you want to store the actual password hash. You never want to store people's passwords. Database admins, developers do not have access to passwords. They never do. So don't be that person, or don't be that developer and do that. We're going to give the varchar status, and it'll be of size 30. If this were the hash, you want to make it, the hash usually is like a lot of characters. It might be like 256 or something. So you could replace 30 with 256 if this were the password hash. But this is just like an actual text password. You can just do 30. This is also going to be not null. Every user has to have a password. It does not have to be unique. I believe password hashes are unique depending on the algorithm and the salt that you might be using. But most of the time, people will type in the same password, so we can go ahead and just let that be the same. In practice, it usually won't be the same though. And the last piece of data we're going to specify is points. So this is going to be an integer, and it will be not null. Every user has to have at least some points, whether that's 0. So remember, 0 is a number, so 0 is not null. So we start to specify not null here. And I did not mean to do that. Okay, so these are all the data for our table. We're not exactly done yet. As you can tell, we're actually getting an error as is. But that's actually because of this comma here. If I got rid of it, it'd be fine. But we're not finished. We need to specify that primary key. And doing so is really simple. You just type primary key with a without a space, or with a space, sorry. Primary key, and you specify what the primary key is. And that's going to be user ID. And we don't put a comma here because that's going to be our last line. And that's it. The command is ready. If we were to go hit run, which in Mysql Workbench is this little lightning here, you can hit that, and there's actually a console down here. It might be small. Oop, not that one. I can't make it bigger, but it's like right here. I don't know why it's so small. It's this literal last line here. If I run this, oh, we got in there. No database. Oh, I forgot to select the database. My bad. We want to select the database too. We made a schema already. We actually have to set that. So what you can just do is just set this as a default schema. So if you do this, this is our default schema. If you were to set one, you can just like double click, and that would also set one. So if you go ahead and run this now, we see that it runs. It says no rows are affected. We didn't insert anything, so no rows are going to be affected. So yeah, whenever you're running SQL commands, you need to select the database. In command line, you have to do this before you're even prompted to type SQL anyway. So this doesn't usually happen in command line, but in a GUI, you need to select one. And again, you can do that by just setting one as default, which I will set this as default for just for workshop purposes. Or you can just double click and I will select that schema instead. You can tell which one's selected if you just look down here. It'll say the schema selected. So if I hit SEC workshop, that's selected. Sys, that's selected, or my daemon schema, that is also selected. So we can go ahead and return to this now. We created the player table, so it was fine here. But what if we accidentally ran this command again? Let's just see what happens if we run it again. We get an error. and it's right here. It doesn't really say what it is. It's kind of small, but if I just go here, where is that? Well, it's not showing. Okay, but we tried to create a table, but this table like already exists. Um, so if I were to go ahead and run some SQL that we're just going to select all, you don't have to do this one. I'm just go ahead and show the table. Select all from what I named the table. Player. Save. Actually, I don't know why I say I don't need to save that. Run the file. Oops. Oh, wrong table. Gotta select that one again. Go ahead, run that. We see here's the columns. We have user ID, the username, password, and points. If I were to go ahead and try to run that, now it shows up. We get this error that table player already exists. And it's right here. You can see that it already exists. You can also see it within here if you you might need to refresh. So if you just right-click tables and hit refresh, it'll show the table here with all the columns listed. And what happens here is that you try to create a table, but it already exists. Remember, computers do exactly what you tell them to do, so it's going to try to create this table regardless if it exists or not. But in SQL, we can specify that if it exists, we don't have to create it. So if you have like some SQL script that's managing your database, you can do create table, and after create table, you can put if not exists. And what this will do is it'll check to see if it exists first, and then it'll create it. So if I try to run this again, which I did, you see I get a warning symbol here, and it says table player already exists, and it didn't change anything. 0 was affected, nothing happened, nothing went wrong. If I were to go ahead and try to drop this table now, again, you don't have to do this, but if I just went to this table right here, right click, hit drop table, if you go drop now, actually I'm gonna do that again because I want to show you the SQL for that. Refresh all again, you don't have to do this. Drop table, review SQL. This is the command that you would use to drop the table. This notation right here is schema.table. So the SEC schema dot table or dot player. So our schema name is SEC workshop and our table name is player. And we'd execute that. That would delete the table. As you can see, it no longer exists. If I run the command that select all from player, we get an error that the table doesn't exist. And if we run our create script again, then we run this again, our table exists now. So that's pretty much the gist of creating tables. We're going to do another table that we're going to create for representing our levels. So we can just copy and paste this. And we can just go ahead and change player to level, level all lowercase. Yeah, I named it levels. And we're going to change some of these values here. So let me just delete this. We're going to have a level ID, which will serve as the primary key for levels. It's going to be an integer, and it will be not null. We want it to have a type. We're going to go ahead and create a name, which is going to be a varchar, all caps, varchar of 20, I believe is the name I use. Yeah, 20 is the size. It's going to be not null. We're going to create a creator, which is going to be the name of the player who uploaded the level. So creator, it's going to be a varchar of 30. This is going to be a varchar of 30 because this will eventually be the link or serve as the relationship between this table here, or will serve as relationship for this table here, and we want it to have the same size in case someone has a username of 30. It'll fit here, and this is going to be not null because this is not null. We don't have to specify not null here. Given that this is not null, this will always be not null. But in the event that you're a database admin and you try to manually edit this table, you want this rule to apply still here too. So we're going to specify not null, and we're also going to specify unique still. In our database application, this won't happen. Like we will never run to a case where there's going to be no creator specified. But again, as a database admin, we could manually insert things to this table, and we want to have the same rules that apply. Next thing we're gonna do is likes. This would serve as the rating for the level. It's gonna be an integer and it will be not null, not null. And same thing for difficulty. We're gonna have difficulty for a level. This will gauge how many points the player gets for completing the level. It'll also be an integer and it will be not null. Actually, it'll be a tiny integer. We want it to be a tiny integer. The reason why we want this to be a tiny integer, our a tiny integer you can think of as like a short, which is a short number. Then in like Java or something. This is going to be a tiny integer because the the game that we're making is going to let users rate level from 1 through 10, 1 being easy, 10 being hard or the most difficult. So that's the only numbers that will exist in this database. It can only be rated 1 through 10. And this will actually be a calculated value. We're going to calculate the average based on the ratings, and we're going to store it here. So that's why we're doing it this way. We're not going to calculate that average now. We'll do that once we actually write the database application, or the application that interact with the database. So yeah, we have that now, and now we can specify a couple of different things about this table. We can specify the foreign key. So remember how I said that relationships need to be linked by some key? So this is sort of how that works. Remember our link here is going to be creators. So players can create levels. So that means that the creator name is going to come from the player table. So that way we can't specify some creator that doesn't exist here. And we do that by specifying foreign key. So we do foreign. I'm not sure if I spelled that right actually. Foreign. Did I spell it right? I actually don't know how to spell foreign. But let me just look here. Yeah, I had it right that time. Foreign key. And we're going to specify an empty set of parentheses, and we're going to put the the data type from this table that will be referenced from the other table. So we're going to put creator here because creator is going to be the one that comes from some other value. And we're going to say references. We're going to put the name of the table that we're referencing from. So we're referencing from the player table and another set of parentheses. And we're going to take the data type that we're referencing from. So it'll be a username. And that's pretty much it for that part. What this pretty much is saying that creator is a foreign key and its value is going to come from the player table and from the username value. So yeah, and that sort of defines our relationship here. This doesn't create like its own table. What this will do is it still creates a relationship. So there's multiple kinds of relationships here. There's can be relationships by table and relationships by value. This is by value because well, technically I guess this could be by table, but this value here is by value because it's not creating some new. This relationship doesn't create some new kind of data. We'll see an example of where a relationship does create some new kind of data, but right here it does not. So we can just do foreign key, creator, and player. That's fine too. And if you remember from the slides, I said that if we tried to delete a value from relationship, it wouldn't work because it was referenced from somewhere else. This applies here as well. If I tried to delete a player that made a level, it would not let me delete that player because they have a level still. We can solve that with one of two ways. We can solve that in our Java application by deleting going through the database, finding every instance of something they own and deleting it first, then delete the actual player. Or we can solve that here with a simple one-line SQL statement. So and that's SQL statement is pretty simple. It's going to be on delete cascade. And what this means is that if this player gets deleted, we're going to cascade through all the potential areas that creator might appear and delete that too. So we can go ahead and that means any variable where creator is set to some reference value here, we're going to delete that entry from the levels table. We'll also specify the same thing for update. So on update cascade, what this means is that if the player changes their name here, it'll also have the name changed here. If we try to change the name here without changing the name here, the SQL command would fail and it would not work. So that's very important for relationships. And of course, we're going to put a comma and specify the primary key. So our primary key here is going to be the level ID. So same thing here, level ID. And that's that table too. Oops, I did not hit that. If we go ahead and run this query, we will get a warning again for trying to create the player table. It already exists, but the other SQL query, the create table, will run, and we can have our player table here. So if I do select all from level, level as in the lowercase level, I run that command. Here's our level table. Level ID, name, creator, likes, difficulty. And if I go ahead and refresh here, we can see our level table here. You can see level ID, name, creator, likes, difficulty, etc. We even have a foreign key specified here now because we specified that player will come from the creator will come from username. This is the player table. So yeah, and we have our on update, on delete cascade. So on update is like a function. So like when the value updates, we're telling it to cascade. Same thing with delete. We won't go over SQL functions during this workshop, but they're pretty self-explanatory. They're much like regular Java function or something. So they're not really extremely important. I don't really find myself using SQL functions much unless you're like a database admin, but that's out of the scope of this workshop. We're going to create 3 tables now. 3 more tables. These are going to represent the relationships between the player and level. So our 3 relationships are that players can rate the difficulty of a level, players can like or dislike a level, and players can complete a level or have progress on a level. So these are all relationships, but they're very different relationships from this one. This relationship doesn't create any new values. There's already a level table. Technically, when you create a level, you're creating a level, but that doesn't need its own table. There's already a levels table, so it doesn't need a new table. But if I were to like or dislike a table, like or dislike a level, we need to store that individual player likes here. And you might say, well, we have likes here, right? So why do we need to store it again? Well, this like refers to the level itself, like the overarching level likes. So like the level may have 36 likes, but which players like this level? Which 36 players like this level? We need to store that somewhere. And we're going to store that in a relationship table. Relationship tables are created the exact same way that regular tables are created. The only difference is that, well, in SQL, there technically really isn't a difference between them. They're the exact same tables. They just need 2 values to relate them by. So you can think of it, actually I'll show it when I go ahead and create this command or create the table. So we can go ahead and, actually I'll copy this one shorter. Copy any one of the create table commands, and we can clear all this stuff in the middle. We're going to go ahead and rename it to, we're going to do, I think I did likes here. Actually, I did rates here. We're going to do rates first. Rates and likes and dislikes are really the same, follow the same formula. The first value we're going to need is the level ID. We need the level ID that the player rated. So this is going to be integer and not null. This will be referenced from the player table up here. So it's going to follow the same formula here. Again, we're specifying not null here because as a database admin, I still want the same rules to apply. In our application, this isn't, if we left this here, this wouldn't really be possible. Like there would never be a entry specified without a level ID within our application. But as an admin, we could always do that. So we want to have the same rules apply. We're also going to want the user ID of the user that rated the level. So we're going to follow the same formula from up here, user ID right here. int not null. We want the user ID rather than the username because remember, user relationships on tables are linked by primary keys. So even though the username is unique, it's not the primary key. So we have to specify the primary keys here. And since this is a table that relates 2 tables together, we're going to specify 2 different primary keys. So one from level ID and one from user ID. Unlike this relationship here that comes from just one table, this only references one table, so it doesn't need a second primary key or any primary key really. It already belongs. This relationship belongs to the level table, so it already has a primary key, being level ID. Whereas this relationship is its own table, so it needs primary keys for the tables it references, which is table 1 being level and table 2 being player. Since a user can rate a level, we need to store the actual rating for the user. So we're going to create rates. It'll actually be a tiny integer. So tiny int, and it will be not null. We're doing a tiny int because the rating will always either be on -1, 0, or 1. -1 meaning that they dislike the level, 0 means that they did not rate the level yet, and 1 meaning they like the level. So, and that gets added into the relationship here is that they will get added into this value here or this value here. Oh, I'm sorry. Actually, we did rates. I was talking about lights. Sorry, rates here. Rates are always gonna be 1 through 10. So, what this means is that someone can use it rated from 1 through 10, being 1 being easy, 10 being hard. So, and these will get averaged out into this value. We'll handle that in our Java application, but that's pretty much the idea of how that will work. So again, this is going to be a relationship table. So we need to specify the relationships that these values have with the other tables. So we're going to do foreign key again to specify a relationship. We're going to do actually I'll make a new line. Oops. We're going to do user ID that comes from here. User actually sorry, this should be a lowercase d. User ID references. We're going to specify the table. It comes from the player table. And we're going to get the user ID value from player. So the user ID value from the player table. We're going to do the same thing we did here. On delete cascade. I'm sorry, caps on cascade. And on updates cascade. We're going to do the same thing again. We're going to go ahead and copy that and paste that. But again, this one's going to be for level ID. So level ID. We're going to have going to specify this to be level ID from the levels table that's here. Same thing here on delete and cascade. And we're going to specify a primary key for this table. Every table still needs a primary key. This one is different though. This one will have 2 primary keys. You might be thinking it doesn't make sense to have 2 primary keys in person for some things or from in practice, but that's actually not the case for relationships. Remember that each relationship needs a primary key. Well, we still need one here. We need at least one. We could get away with having one, but as a developer, you want to be clear as possible to what things are. And technically, these are both primary keys. So we're going to specify them as both primary keys. So we can do level ID, comma, user ID. And that will specify these both are primary keys. That's perfectly legal. And your database won't crash if this happens. Sorry. So that's our relationship for that table. If we were to go ahead and run this command again, we're going to create a table. Oops. Oh, sorry, I spelled that wrong. Where did I spell it wrong at? Which one did I spell wrong? Oh, it's this. Sorry, this should be level. So this here I specified as player. It should actually be level. My bad. Stop hitting save. If I run it again, we see here that it works. We got 2 warnings from these statements up here, but the last one will run. And if we go ahead and select all from, I think I did rates. Here's the rates table. Has the level ID, the user ID, and the rates. If we were to picture this in our head, this is going to be a many-to-many relationship. So many users can like or rate many levels. So there'd be a lot of repeating values for level IDs here and a lot of repeating values for user IDs here. So there could be, let's say, I don't know, a level ID of 1 could have 4 different values here, and a level ID for 2 could have like 3 different values here. So there could be like 4, 4, 4, and different values. 333 in different values. And those values can repeat here and here as well. So that's sort of what that means in design. We're gonna go ahead and create the rest of the relationships. We have likes next. We're gonna call that one like and dislike. We're just gonna copy this table here. These relationships will look the same. So we do create table if not exists. We're gonna name this likes, dislikes. This stuff will stay the same here. The level ID, user ID will stay the same. First one, name this one to be like count. This stuff right here will stay the same. Oh, sorry, I should make this lowercase, lowercase. This stuff here will stay the same. This stuff is going to stay the same too as well, actually. None of these really change. The only thing that really changes here is this one. We're gonna have one more. Is like count tiny integer? Make sure. I want to keep my data types consistent. It is. Yeah, it is. Okay. So, I'm gonna keep these consistent as well. Yeah. Okay. Actually, we're gonna make a small change. Just to demonstrate something when I go ahead and do the Java application. We're gonna move the not null values from here. So, if you have for rates and like count, remove the not null. That way I can show something off cool when I do the Java application. We're gonna go ahead and copy this again and paste that down here. Our last relationship is going to be for percentages. This is going to represent the how much level the user's completed. So for each level, a player could have some percent that represents how much level they completed. So player 1 could have 50% on the level. Player 3 could have 100% on the level, meaning they beat the level. Player 5 may have 0% on the level, and player 273 may have 36% on the level. So we can go ahead and do percent right here, which is going to be a tiny integer. And again, this stuff here will stay the same. And that sort of like creates all the relationships here. So we have 3 relationships by tables. We have 3 table relationships, and 1 value relationship here, and 2 distinct tables. So if we go ahead and run this again, we get our warning commands, and our other tables here get created. So we go ahead. Let you run it again. There we go. We go ahead and we can go do select all from. I believe I called it likes, dislikes. Yeah, like dislikes. I think I spelled that right. I did. Here's like dislike table. Percent shows our percent table. Oh, is it not percent? Percentages, my bad. Percentages. Percentages. That shows our percent table, and that's pretty much our entire database scheme. It's done. We've created an entire database schema. It's very short just for this one. Let's go ahead and refresh this here. If we go to tables, right click, refresh all. We see all of our tables. We can use Mysql Workbench to get a diagram of this table. It's not really beneficial, I've heard, because it's very hard to see like it in diagram wise. But let me go ahead and get that diagram for you guys. Pause that. I'm gonna go ahead and open this one. I'm also going to head open this one too, just to share something for fun, if I find it. Maybe not. Oh, there it is. Okay. Oops, not that one. Sorry, just let me go ahead. Okay. So if we go ahead and just take a look at this. This is the schema that we created. So we have our players table here. We have our levels table here, and all of our relationships here. So as you can see here, there's a link between this table, the player table, and the rates table. This shows a relationship. So level ID is related to levels. User ID is related to users. likes and dislike has a table here, a relationship here as well. There's a relationship here from levels and percentages. This dotted line here, it's kind of hard to tell. This dotted line is not connected to the likes or dislikes table. It's actually connected to levels and players. It's just underneath of this for some reason. But what this shows is that value relationship between the username and the creator here. That's what this dotted line means. It shows value relationships, whereas solid lines show table relationships. So that means you can read, if you were to read this in person, this would be read as players can rate levels, and players can, well, this is percentages, but players can complete levels or play levels. Players can like and dislike levels, or players upload levels. So that's what this relationship here is showing. Can I actually mark this up? I don't think I can. I think I can. I can. Oh no, I can. Annotate. Can I just like? No, I can't. Oh, well, whatever. Anyway, so oh yeah, I can. It's right here. Let me go ahead and draw that. So players can rate levels. That's one. Players can complete levels. Players can like levels. It's another one. And players create levels. So that's just an example of the relationships we have going on here. And this is a very small schema. You know, it looks small. It is small. It wasn't very complicated to make this. But as a database admin for enterprise scale applications, database schemas can get very complicated very fast. For instance, this is our schema, but let's take a look at the schema for a enterprise application known as Jira. This is it. So this monstrosity is the database schema for Jira, which is a ticketing application that used to track work. Typically, people who are on like a job or internship will use this to track work, see where they're going. So this monster schema here is how the backbone of how Jira works. So there is a lot of relationships going on here. There's some table ones or solid lines. There's some value relationships here. See if I can zoom in actually. Will it actually show me? Yeah. So we see there's some data types here. There's some very large values here for the text. Specifying as a table. I cannot find. See if I can find primary keys here. I don't think they specify primary keys, but you can sort of figure out what a primary key is by looking at looking at these. Like project ID is probably the primary key for this one. ID probably the primary key. These are table names. Like JiraDB is a schema name dot table name. So there's a lot going on with the Jira database schema. They can get massive really fast. So yeah, that's pretty much it for creating tables. We can go ahead and try to insert some test data if we'd like to. I want to go ahead and open some up just because I have some ready. So let's say we can just go ahead and remove this. Let's say we want to insert a new player. Remember I said the common SQL command. Let's do insert into. We're going to specify the player table. And remember I said we could do. Remember I said earlier we could specify like column names. We can do that if we'd want to. So we can do like columns. I don't remember what they are actually. We have user ID. Excuse me. User ID, username, password and points. And then we can go ahead and do values. And then we have to specify the values here in order that we gave it here. So the user ID can do 1. Username can be a string. It would be like test. The password can be Apple with lowercase because we don't care about security. And the points can be 0. They're not going to start with any points. And we can go ahead and run this command. Did I run it? No, I didn't. We can go ahead and run this command. We get a check mark. And if we go ahead and try to select from the table again. Let me just undo all this because I had that command earlier. So length all from player. We go ahead and run that. We can see an entry value here. We have the user ID, the username, Apple, the password, and points. Again, you don't want to see the password. You probably mostly the hash, but as a database admin. But yeah, again, we don't really care about security here. We're gonna go ahead and insert some other players. I want to demonstrate something. Insert into player. We don't need to specify that value thing like it did before. We could just insert into players and just do values. If we do it this way, we have to keep it in order as specified here. So if you did it the other way, it allows you to change the order up. But this way, you have to specify in the order, sort of like shorthand. Why is that there? It's sort of just shorthand for it. So we can do 2. Remember, the user ID is unique. Remember, username is also unique. What was my username? Test. We're gonna do writer. Password. Again, those are not unique, but we're going to have a different password anyway. We can do apricots with a capital A or apricot. We can give this guy a points. He has 10 points. He's beating a level or some. We can insert multiple players, so we just copy this and we paste that. We can go ahead and do 3. Oh, sorry, semicolon that. SQL commands ended a semicolon, by the way. We can do that uniquely. Let's do, I don't know, dot. Apricot, because again, security is not important. 15. I did not mean to hit save. And if we run that command, these will insert 2 of the players at the same time. And if we do select star, which is all from player, and we go ahead and run that, we list all of our players. We can do a lot of cool things though with SQL, like where, for instance. We can do where user ID equals 1, and if we run that one, that gives me just 1 user. Or we can do, again, most people wouldn't do this, but we can do password equals apricot. We run that. We get users 2 and 3 because they have the same password. Or we can do, actually, I'll change the user ID. I'll change it back to user ID equals 1. All right. User ID equals 1. Instead of doing select everything, we could just do select the username, which would just return only the username, nothing else. Or we can do select password, which would return only the password. What if we try to do something that doesn't exist? I don't know. Let's do tie. Tie doesn't exist. We get the error unknown column tie in field list. So that's the beauty of SQL querying. We can do really powerful queries because our data is organized. Why is it not working? What? I'm sorry, I'm not sure that's not working. User ID equals 1. Did I say that wrong? Track the. Strange. I don't know. Why it's not working. But anyway, but it doesn't matter. I did it again. Oh, now it's working. Okay. Well, anyway, I don't know why that happened, but either way, that's pretty much the gist of SQL and why it's very beneficial. Our data is organized. We can easily sort through this. And what this means is that if we can easily sort through this, our applications can easily sort through this. So we're going to create a very interesting application in which we interact with this database to simulate data transfers between a game. This will simulate the backend of a game, the backend web aspect of a game at least. So yeah, that pretty much wraps up everything I have. Actually, I wanted to show something else really fast. I guess I can show this schema. This will represent the password better. This is from my own personal project. So I believe the tables I have here are users. Yeah, select all from users. If I go ahead and select everything from users, what this will do, well, it's null right now, but as you can see, I have a user ID, username, password hash. I'm clicking these, and an email. This is just for users. And this, although looks like it's something that you can create from just regular SQL commands, it's actually managed by scripting. which is what you can do with MySQL Workbench is this file here. You could save it as some SQL script and manage it. How you integrate that depends solely on your application of choice or your language. So it'd probably be different from a Java application compared to like a Rust application or something. But but that is also something you can do if you were into database administration. Um, but yeah, I think that will wrap it up for everything we have. Next time we meet, we're going to go ahead and work on making a Java application that will interact with this database. It'll be a console based. If you're participating in that, you're going to need Java 15. That's recommended. That's what I'll be using. You'll need the Java database connector, which is JDBC. It's just a jar file. You can add that to your class path. I'll go over how to do that during the workshop as well. Um, you'll need an IDE that's preferably not Dr. Java. I recommend using Eclipse or IntelliJ because I'm familiar with how to add jar files to the class paths for both of them. I'll be using IntelliJ, but Eclipse works just the same, really. Um, so yeah. Um, if there's no other questions, that is all I have for his workshop.